Alright, gang, here we go. This is for Chem 1, Unit 9. Part 1, we're talking about kinetic molecular theory today. Super fun stuff. Alright, so start of a new unit. Time to learn some new things. Alright, we'll be done with the math for just a little bit. Alright, so if you were sick and tired of stoichiometry, now's your chance for a break. Alright, so states of matter. We're going to talk about kinetic molecular theory here. All right, kinetic molecular theory, in essence, gives us tools to predict the behavior of gases at certain conditions, okay? And so in order to use this kinetic molecular theory, we're going to make 5 assumptions, okay? And I have no idea. I just noticed why the PowerPoint made these guys all number 1s. I wonder if it did that on the... Nope, those are 4 and 5. I don't know why they were 1s. But anyway, so there's 1, 2, and 3. Okay, so essentially what we're saying is we're going to have 5 assumptions, and these assumptions will help us predict the behavior for gases in different conditions. All right, and so we're just going to go through these assumptions, and then we're going to look at a model here and see if we can. It'll help us figure out exactly what this all means. Okay, so number 1, gases consist of large numbers of tiny particles that are far apart relative to their size. Volume of gas particle is considered negligible. Okay, so essentially what we mean is that the gases are consisted of large numbers of tiny particles. Okay, tiny particles. So, and you guys understand this. There's billions and billions of molecules. Like, even if you just blew up a balloon, you'd have billions of molecules, right? Or atoms or whatever it was that filled up your balloon, right? Even just a little bit. So any gas container you have of any appreciable amount is going to be large numbers of these particles. Okay. Now the interesting thing, like, that just makes sense, right, based on what you've learned about chemistry so far. But the interesting thing is that in the kinetic molecular theory, we make the assumption that the volume of these gas particles is considered negligible, and specifically, this is negligible when compared. Okay, when compared to the volume of the container. Okay, volume of the container. All right, so if you, like, in the average classroom, okay, if you took your all the gas that's in there, brought down the temperature of the room super cold so that all the gas liquefied, right, it all condenses and it all liquefies, your all that gas would be less than a millimeter thick across all the parts of your surface of your classroom. Okay, so like there's vast amounts of empty space between these particles. Okay, and so these gases, we can assume, because they're so tiny compared to the space they're taking up, that their volume of the gas particle is negligible. Okay, negligible means that we can ignore it. It doesn't mean it does not have volume. It just means that we can ignore it because it's such a small percentage. All right, number 2, gas particles are in continuous rapid random motion. Okay, so that means, so we got these particles, and essentially what they're doing is, we imagine that they're like billiard balls. They're bouncing around, bouncing off each other all the time, ramming into each other, bounce, 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 and that's essentially what they're doing. And it's continuous, it's rapid, and it's completely random, just based purely on what they're hitting, and then they go off their own ways, so on and so forth. All right, now because they are moving, they have kinetic energy. Remember, kinetic energy is the energy of motion. All right, and we'll talk more about kinetic energy here in a second. And essentially what this is saying is gases will fill their containers. Okay, so if you stick and this makes sense. This is something you learned probably in 3rd grade science. Your gas is going to fill up whatever the container is. It doesn't just sit at the bottom like a liquid. It's going to fill the entire container. Number 3 says collisions between gas molecule particles and between particles in container walls are elastic collisions. That's what this last word says, collisions. All right, so if you've ever seen, like, the Newton's cradles is those guys that's got, like, it's got 2 beams that go across like this, and then it's got all these balls, right, that sit there like this, and they're attached to strings, right, like this. And then you pick one up, and then you drop it, and it goes tick, and then the other one goes whoop, and then goes tick, and then up and tick, right? And this will last, if it's a really well-made Newton's cradle, this will last a really, really long time, okay? Because these collisions are completely elastic, right? No kinetic energy is lost. All right, now if your Newton's cradle is no good and there's gaps between them like in mine here, or if it's not quite completely level, then you're going to lose kinetic energy. It's not going to last nearly as long as your elastic, or your collisions are not nearly as elastic. All right, so elastic collisions, all right, are an important part of the kinetic molecular theory. So we assume that these collisions maintain their kinetic energy. So if you think about billiard balls, if you've played pool, right, you hit the pool balls and they fly forward, and when that Y1 hits the big triangle mess of them, it rams into it and breaks it up, right, and then they kind of go everywhere from there, right? And so that's essentially what's going on with our molecules. Only the difference is with billiard balls, they'll eventually slow down and stop because of friction. With the kinetic molecular theory, we assume that there's no friction, right? Because there's literally nothing there for them to run into because they're so small, and so therefore these kinetic molecular, or these collisions are just going to last forever and ever and ever and ever and ever and ever and ever. Okay. Number 4, there are no forces of attraction or repulsion between gas particles. So essentially we're saying there's no intermolecular forces. So they don't stick together and they move independently from one another. Okay, and so these molecules, they just act like billiard balls, right? And so they just run into each other, bounce off each other, and they kind of hit the walls and then each other and keep going around and around and around. And so there's no intermolecular forces that are acting on these balls. All right, so if we did have intermolecular forces, it would almost be as if you had these billiard balls, but you put magnets in them. And so sometimes they would stick together or they would push each other off, okay? So on and so forth, okay? And then number 5 says the temperature of gas depends on the average kinetic energy of the particles of the gas. Okay, so this is key. So we can actually get an idea of the kinetic energy of our molecules, okay, by just taking the temperature. The higher the temperature, the faster they move, and therefore the more kinetic energy they have. All right, so it says here kinetic energy is equal to 1/2 mv squared. M is the mass, and v is the velocity. Okay, so essentially what we're saying is that all these molecules are going to have, if we're at a given temperature, all the molecules at that temperature have the same kinetic energy. Okay, now, but will they all be moving at the same speed? No, they will not be moving at the same speed, and part of that is because they all have different masses. Okay, and remember, they'll have the same kinetic energy, but their masses will be different. And notice that it's also their average kinetic energy. Okay, you can imagine pool balls, sometimes when they bounce around, okay, there might be an occasion where a pool ball was going very, very fast, and then it hits a ball, and then it tends to stop for a second until something else hits it. Same thing happens with our molecules. So we're not talking about individual speed of individual molecules. We're talking about the average speed of all of the molecules. Okay, and so since we're literally looking at billions and billions of these molecules, then it all kind of works out in the end based on statistics. All right, so to kind of give us a better idea of what this all looks like, we're going to look at this thing over here. All right, so this guy here, this is the PhET, states of matter, and here we got a solid, neon solid. So we're going to jump to neon gas. So here's our gas molecules, and they're bouncing around in here. Okay, and you can see we're at a really low temperature, 55 Kelvin. That's pretty cold. That's pretty cold. Okay, so that's at like negative 220 something degrees Celsius. All right, so negative 200 300 in Fahrenheit or something like that. All right, so anyway, but since we're so cold, you can see that some of these particles are actually hitting each other, okay, or actually sticking together a little bit. So our kinetic molecular theory doesn't work very well at really cold temperatures. So let's heat it up. So we're going to add some heat here until we get to about room temperature. And you notice that as I'm increasing the temperature, that the molecular motions of these argon particles, okay, should be speeding up on average. Now, some of them, they might reach a case, like pick one and follow it for a second, and you'll see that that one particle sometimes moves really, really fast, and then sometimes it moves really slow or stops even, just depending on what it hit, what's going on around it. All right, so just pick one and look at it and see, and then just kind of take a gander. Now notice, like, they're hitting the walls of the container, they're hitting each other. It's just completely random. You know, that's just kind of what it does. All right, we're getting close to room temperature here. All right, 298 is about what we want. So notice that our molecules are significantly faster now than they were at 55 Kelvin. All right, 2, 3, 4, 5, 6, 7, 8. Nailed it. Okay, so look how fast these guys are moving now. So we got a lot of molecular motion going on, and it's all dependent upon their kinetic energy, right? So they hit each other. So this is pretty fascinating. This is just the PhET states of matter. So if you just Google PhET states of matter, you can play with it. You can play with all these guys here and change them to different substances. They've also got phase changes, which is another cool demo worth doing. All right. We also need to talk about some physical properties of gases. All right. Whoops. So physical properties of gases, these are pretty easy. First one is expansion. Should be gases do not have a definite shape or volume. They can take the shape of their container, super easy. All right, this is third grade science right there. They also have fluidity. Now this is probably a new term to you. This implies that our molecules can flow past each other. In science, whenever we talk about fluids, really we don't just mean liquids. You probably used to, your mom said, drink your fluids, you know, so on and so forth. But fluids in science are liquids and gases. So both of these things working are both fluids. Okay, so gases have fluidity because their molecules can slide past each other just like a liquid. All right. Gases also have really, really low density. Okay, the density of a gaseous substance at atmospheric pressure is about 1/1000th the density of the same substance as a liquid or solid. Okay, so the gases are ridiculously low density compared to solids and liquids. That's why it's really easy to walk through a gas. Like if you just think about how much energy does it take to walk through your room, right, from one side to the other, and you don't really have to worry about pushing against the air, right? It just kind of moves out of the way because the vast majority of it is empty space and it's not hitting you very hard. Now when it's windy, those little gas molecules are hitting you and slowing you down. You have to fight against that force that they're applying on you. But just standing there, it's vastly empty space. Now think about what it would be like to try to walk through your table, right? And be a lot harder, and that's because they have a lot more density. Okay, gases are also compressible because there's lots of empty space. There's lots of space for you to push those gas molecules closer and closer together. So they're usually really far apart, but we can crowd them close together by putting them under pressure. Okay, under pressure, whatever. Okay, diffusion and effusion. All right, diffusion is the mixing of gas particles of two substances from random motion. So this is like somebody in the corner let one rip, right? They just let out a little toot. And then somebody on the opposite side of the room will eventually smell that toot, right? That fart right there. They're going to smell it because the gas diffused from their little stink area over there in the corner to wherever you're sitting. Right, and so that's diffusion, is the spreading of a gas. And a less gross metaphor would be like if you're at home, right? And you're somebody's cooking dinner and you can smell that gas, right? Or you can smell whatever they're cooking before you actually make it, right? Effusion is when your gas molecules go through a tiny hole. So if you've ever been to like Red Robin or restaurants where they, like as a little kid, where they give you like a helium-filled balloon, when you're done, right? You probably took that thing home and you played with it. You saw how it kept floating. It's pretty exciting, right? And then you tied it to a toy. You went to bed, and then you woke up the next day, and the balloon it's still inflated, but now it was just sitting on the ground. It's not floating anymore, right? It's like all the helium left, and that's because the helium did leave. Even though latex balloons look like they're completely solid, they're actually full of tiny little pores, and then those pores are just small enough or big enough that helium atoms can fit through it. And so eventually over time, all the helium will escape out of the little holes in your latex balloon, and all the helium leaves, and then therefore now your balloon is no longer helium balloon, it's just a normal balloon and it doesn't float. Okay, so that's diffusion and effusion. So here's just a little graphic. So here's your diffusion going on your left, and then your effusion is when those guys travel through that little hole over there. Last thing here in part one is ideal versus real gases. Okay, ideal gases are gases that essentially follow the kinetic molecular theory to a T. All right, so these are the things. So we remember we started off by talking about those 5 assumptions we make. If the gas follows those 5 assumptions, and then we call it an ideal gas. Okay. Now, the vast majority of gases out there are not completely ideal. All right, most of them have some real behavior, right? And that's because they're real as opposed to these ideal gases. Okay, so real gases do not have perfectly elastic collisions. Okay, so they hit each other, and we saw that when we looked at the neon. Some of them would stick together and kind of get bounced around each other as they moved across the screen, and then even in some cases, you could have, depending on what your gas is, you could not only have attractive forces, but you could have repelling forces, right? So it'd be like 2 magnets of the same charge or the same pole being next to each other. Okay. They also have weak intermolecular forces. All right. We just kind of talked about that. And then they do, in fact, have small volume. All right. So really, we have to watch out for the difference between ideal and real gases when we are at low temperature, because at low temperature, they have the intermolecular forces can play more of a part. And then at high pressure, because at high pressure, the percentage or the ratio of the molecular volume to the container volume is much bigger. All right, and so those are the 2 conditions, so low temperature and high pressure. And that's it for part 1. Do your practice problems. Let me know if you have any questions, and I'll see you on the flip side.